Empirical formulas, remember, are the simplest whole number ratio of atoms and elements in a compound. So basically what that means is our chemical formula is in lowest terms. The reason that this is important is because if we do elemental analysis in the lab, we can break down our compounds and determine the masses of each of the elements formed. And so from that information, we can get our empirical formula. There's lots of ways that we can do this. We can do it by decomposing the compound. We can do it by combustion analysis if it contains carbon and hydrogen. Or we can figure out the percent composition. But all of this information allows us to determine the empirical formula. So how do we go about finding the empirical formula? We're going to start by, if we're given percentages, converting them into grams. So we can do that easily if we just make a simple assumption that we are starting with 100 grams of the compound. Then our percentages just become the amount in grams. If it's already in grams, you do not have to make this assumption. You can start directly with the grams. You convert the grams to moles, and we do that by using the molar mass of each element off of the periodic table. We use the units to get from our grams into moles. We write a pseudo formula, and so pseudo means fake. The reason that it's fake is because we are going to have decimals in our moles, and we can't have that in a real formula because it has to be whole numbers. But we write the amount of moles as a subscript to help keep things organized. From there, we're going to want to find whole numbers, and the easiest way to do that is to divide by the smallest number. This allows us to turn at least one of the numbers into a whole number of 1. If the other resulting numbers are within 0.1 of a whole number, we can round. So if it gives you something like 0.9 or 1.9 or 1.1, you can round to the closest whole number. If we get a number that is 0.5, we need to multiply all of those subscripts by 2 in order to make it a whole number. If it is something closer to 1/3 or 2/3, we need to multiply by 3 to make it a whole number. Or if it is 0.25 or 0.75, we multiply by 4 to make all of the subscripts whole numbers. If everything is a whole number at this point, we can skip this step. So let's look at an example. We have a compound that we've undergone laboratory analysis. We determined the following composition. We want to find the empirical formula. So it's 60% carbon, 4.48% hydrogen, and 35.53% oxygen. The way that we start is we start by making our percentages whole numbers. So if we have 60% carbon, that is going to become 60 grams of carbon. If we have 4.48% hydrogen, that's going to become 4.48 grams of hydrogen. And our 35.53% oxygen is going to be 35.53 grams of oxygen. So we are just assuming that we're starting with 100 grams to easily convert those percentages. Now we want to find the number of moles. In order to do that, we're going to multiply by the molar mass off of the periodic table. I'm going to do these problems in parallel just because we follow the same steps for each element. So carbon, if we look at the periodic table, has a molar mass of 12.01 grams. We want the grams on the bottom, so it cancels with the grams in our problem. Hydrogen has a molar mass of 1.008 grams for 1 mole of hydrogen. And oxygen, 16 grams for 1 mole of oxygen. Now we can do our math and calculate how many moles of each one we have. Our next step is to write our pseudo formula. So we're going to write these moles as subscripts. This helps us keep our problem organized and allows us to see it as a chemical formula. Next, we are going to take and divide by the smallest number. In this case, our smallest number is oxygen. So we divide each one of these numbers by the moles of oxygen. This allows us to find that oxygen has a subscript of 1. If we divide our hydrogen, we're going to get 2. And if we divide our carbon, we end up with 2.25. Now we're not quite done with this problem because these are not all whole numbers. So we need to multiply each of those subscripts by a number to make them a whole number. In this case, because it is a 0.25, we're going to multiply each of the subscripts by 4. So we end up with C9, H8, O4. And that would be our empirical formula. Your turn. Try to find the empirical formula for ibuprofen. Pause the video and determine the empirical formula. So again, we're going to make our percentages into grams for each of our elements. We're going to convert the grams into moles using the molar mass. For each of the elements. These numbers come off of the periodic table. We can do our calculation. For each of the elements. Our significant figures are not quite as important in this type of problem because our goal is to find whole numbers. We write our pseudo formula. want to keep enough significant figures that we don't end up with rounding errors, but the exact number is going to turn into a whole number. We divide by the smallest value. And we end up with 6.5 carbon, 9 hydrogen, 1 oxygen. In order to make this a whole number, because we have a 0.5, we're going to multiply the formula by 2. End up with C13, H18, O2 is the empirical formula for our ibuprofen. Empirical formulas are helpful, but they are not the full story. For molecules, we want to figure out the molecular formula. The molecular formula is always going to be a multiple of the empirical formula. In order to determine the molecular formula, we have to know what that empirical formula is, or have a way to find it out, and we need the molar mass of the compound. By having the molar mass, we can compare that to the empirical mass, or the mass of the empirical formula. This allows us to find what that multiplication factor is for the empirical formula to turn it into the molecular formula. We just find that by dividing the two masses. The larger mass of the molecular formula always goes on top, so we end up with a whole number multiple. So here's an example. We want to find the molecular formula for butadiene. If we know the empirical formula and the molar mass, we want to find the molecular formula. To do this, we're going to calculate the mass of the empirical formula. I'm going to represent empirical formula as an EF. So we're going to take 2 times the mass of carbon plus 3 times the mass of hydrogen plus 1 times the mass of oxygen. This will give us the empirical formula mass, in this case 43.04 grams per mole. In order to find our multiplication factor, we're going to take the molar mass of the compound and divide by the mass of the empirical formula. In this case, 86.03 grams per mole divided by 43.04 grams per mole. The smaller mass is always on the bottom. We do this division, and again we're looking for a whole number, so if it is close you want to round it. We find that our multiple is 2, so we're going to take our empirical formula and multiply each of those subscripts by 2 to find our molecular formula. Here's one for you to try. Pause the video and determine what the molecular formula is. Let's start by finding the empirical formula mass. So we have 5 times the mass of carbon from our empirical formula plus 3 times the mass of hydrogen. This gives us a mass 63.08 grams per mole. We're now going to compare it to the mass, the molar mass of the compound, to that mass that we just found of the empirical formula. So 252 grams per mole for our molar mass compared to 63.08 grams per mole. That gives us a multiplication factor of 4. So our C5H3, we have to multiply those subscripts by 4. C20H12 would be our molecular formula.